Hello everyone, my name is Zipan Liu. I am a postgraduate student at Shenzhen University. Today, I will present our CVPR2026 work, titled VesMamba, 3D Pulmonary Vessel Segmentation from CT Images by Mamba with Structural Perception and Scale-Aware Filtering. 3D pulmonary vessel segmentation is a highly challenging task. On the one hand, pulmonary vessels have complex tree-like structures with significant scale variations. On the other hand, in CT images, small vessels often have low contrast and are easily affected by motion artifacts and complex background tissues. In addition, different pulmonary structures in CT images can exhibit high similarity and complex overlap. CNN-based methods are good at extracting local features. However, they struggle to model the long-range continuity of vessels. Transformer-based methods have strong global modeling capability. However, they introduce high computational costs in 3D CT images. Therefore, we aim to leverage the efficient long-range modeling capability of Mamba, while enhancing the model's perception of 3D vessel spatial structures. In recent years, many methods have been applied to tubular structure segmentation, such as the CNN-based method DSCNet. DSCNet uses dynamic snake convolution to simulate tubular structures and incorporates topological constraints to improve structural continuity. However, CNN methods mainly focus on local feature extraction. For pulmonary vessels, which have long-range dependencies and complex tree-like topology, CNN-based methods still struggle to fully model the global vessel distribution. Transformer-based methods, such as MPT, make transformer patches better fit vessel structures to preserve vessel integrity. However, transformer-based methods usually introduce high computational costs, which limits their application in 3D medical images. Mamba has been introduced into 3D medical image segmentation due to its efficient long-range sequence modeling capability, such as VesMamba. However, standard Mamba needs to flatten 3D image features into sequences for processing, which disrupts spatial relationships and makes it difficult to fully perceive the local structures and spatial anisotropy of pulmonary vessels. To address this issue, we propose VesMamba. This is the overall architecture of VesMamba. The model first uses a hierarchical encoder to extract 3D features at different scales. Then, we propose the BSF module to perform bidirectional fusion and noise filtering on the multi-scale encoder features. At the high layers and the bottleneck, we introduce the SSP module. SSP uses Mamba to model long-range dependencies and further incorporates spatial structural perception to better capture the tree-like structures of vessels. Finally, NC decoder directly constrains low-layer predictions using the vessel contour and position information provided by high-layer decoders, thereby improving segmentation consistency and accuracy. 3D vessels exhibit spatial anisotropy. Specifically, along the vessel direction, vessels show an elongated morphology, while in the cross-sectional plane, they show an elliptical morphology. Traditional convolution operations perform the same operation along each spatial direction, making it difficult to effectively capture these anisotropic features. Therefore, we designed the Dynamic Spatial Attention Convolution, or DSAC. Specifically, we first use three-direction separated convolutions to extract spatial features along the X, Y, and Z directions, respectively. Then, we concatenate these three-directional features and generate directional weights through global pooling and convolution. Finally, we apply softmax to obtain normalized directional weights, and use them to perform weighted fusion of the three-directional features. In this way, DSAC can better capture the distribution and spatial anisotropy features of 3D vessels. We further propose the Spatial Gated Structural Perception Module, or SSP. Specifically, the SSP modules in the encoder mainly consist of two parts, SGM and self-attention. In SGM, the upper branch uses bidirectional Mamba to model long-range dependencies. The middle branch uses convolution to extract local features. And the lower branch uses DSAC to extract the spatial structural features of vessels. Then, we use a gating mechanism to reweight the Mamba features with the spatial structural information obtained by DSAC. In this way, Mamba can perceive vessel spatial structures while performing long-range modeling. Finally, self-attention is applied to further enhance the long-range dependency modeling capability. In addition, for the SSP at the bottleneck, we replace self-attention with MSAG. MSAG uses the multi-scale encoder features enhanced by BSF to guide the deep features, enabling the model to further focus on vessels of different scales at the highest semantic level. The second key module is the bidirectional scale-aware filter, or BSF. In pulmonary vessel segmentation, low-layer features contain more detailed information, while high-layer features contain stronger semantic information. If these multi-scale features are directly fused, they may interfere with each other. Therefore, we design BSF. It first performs bidirectional feature fusion, so that the fused features contain both local details and global semantic information. Then, the fused features are used as a filtering gate to reweight the original encoder features. In this way, BSF can highlight the useful information in the original encoder features. Traditional deep supervision usually computes losses separately at different decoder stages, which may lead to inconsistent predictions. Moreover, high-layer decoders contain stable vessel position and contour information, while low-layer decoders preserve richer details, but are more easily affected by noise. Therefore, our proposed MC decoder uses high-layer decoders to directly constrain the predictions of low-layer decoders, reducing the inconsistency among different decoding stages. In the experimental section, we used 3D pulmonary CT datasets. The first one is PARS-22, a public dataset for pulmonary artery segmentation. In this work, we use 100 publicly available cases from this dataset. The second one is Lung-79, our in-house dataset, which contains 79 CT scans for simultaneously segmenting 3 structures: arteries, veins, and airways. Here we present the visual comparison results between our method and other state-of-the-art methods. In the figure, green indicates correctly segmented regions, yellow indicates false positive regions, and red indicates false negative regions. We can observe that, compared with other methods, our method significantly reduces both false positive and false negative regions on PARS-22 and Lung-79, especially in small branches and complex crossing regions. In the quantitative experiments, we compare our method with various state-of-the-art methods. Our method achieves the best results in terms of DICE, centerline DICE, HD95, and NSD. Specifically, DICE, centerline DICE, HD95, and NSD evaluate overall segmentation accuracy, connectivity, spatial similarity, and surface alignment, respectively. These results demonstrate that VesMamba is not only effective for single-target vessel segmentation, but can also handle more complex multi-target segmentation tasks. Here we present a visual analysis of the intramodule ablation results. From the left figure, we can see that after adding SSP, the model focuses more accurately on vessel regions. In particular, it better attends to vessel structures while reducing interference from non-vessel regions. The red figure shows that after adding BSF, the model achieves more stable segmentation for vessels at different scales, with fewer false negative and false positive regions. We conduct both intramodule ablation studies and intramodule design ablation studies. From the intramodule ablation results, we can see that adding SSP brings the most significant performance improvement, indicating that spatial structural perception is crucial for 3D pulmonary vessel segmentation. After adding BSF, the model performance is further improved. Finally, with MC decoder, the model achieves the best results. In the intramodule design ablation studies, we further verify the effectiveness of specific designs, such as DSAC, MSAG, and ShiftConf. The results show that these designs jointly contribute to the performance improvements of the 3 proposed modules. Finally, I will summarize our work. We propose VesMamba, a Mamba-based model for 3D pulmonary vessel segmentation. First, the SSP module combines DSAC with Mamba, enabling Mamba to perform long-range dependency modeling, while also gaining spatial structural perception. Second, the BSF module uses bidirectional multi-scale fusion and gated filtering to suppress noise in encoder features and enhance vessel-related features. Third, MC decoder directly constrains low-layer predictions using high-layer decoders, thereby improving segmentation consistency and accuracy. Of course, our method still has some limitations. It may struggle when vessels contain excessive branches, or when the target morphology is abnormal and irregular. That concludes my presentation of VesMamba. Thank you for watching.